Students, in the last class we discussed about Young's double slit experiment. Today we are going to discuss about lateral displacement of fringe or fringe shift due to introduction of thin film. The thickness of thin sheet of transparent material such as glass or a mica can be determined by employing biprism experiment. If a thin transparent sheet is introduced in the path of the one of the two interfering beam, the fringe must get displaced towards the beam in whose path of the sheet is introduced. By measuring the amount of displacement, the thickness of the sheet can be determined. So just observe the diagram here. These are the two sources S1 and S2, and this is T and this is screen Y. The distance between the screen and slit is D. Initially, let S1 and S2 be virtual coherent monochromatic source. The point O, this is point O, is equidistant from the source, that is slit S1 and S2. So the path difference here become S1 O is equal to S2 O. So this path difference of this S1O and S2O is equal here. Let transparent plate G of the thickness T and having a refractive index mu is introduced on the path of the one of the beam. Here we introduce this sheet in between S and screen Y. So this alters the path, or that is optical path length of SO and S2O. Therefore the central bright fringe, here we get a central bright fringe, shift towards the point P from O. This is point free P. So this central bright fringe is shift from O to P. So the light wave from S to P, that is S to P, travels partly in the air and partially in the sheet G. The distance traveled in the air is S P minus T. This is the thickness of the sheet. And optical path we can express as here delta SP is equal to SP minus T, that is the path traveled by the light in air, that is SP minus thickness T, plus mu into T, where mu is the refractive index. So we can express this equation as SP plus mu minus 1T. Because here TT is common, so take SP outside the bracket, so S1P plus of plus mu 1 minus of T. Again, path traveled by the S2P is, we can express as it is delta S2P is equal to S2P. So the path difference of the light travel from S to P and S2 to P we can express as, that is delta S1P minus delta S2P is equal to 0. So we can express this equation as delta S1P is equal to delta S2P. So substitute the value of delta S1P and delta S2P. So value of delta S1P is S1p minus t plus mu t, or S1p plus of mu1 minus t, and value of S delta S2p is S2p. So after substitution the value, here we get S1p plus mu minus 1 of t is equal to S2p. So take this S1p to right hand side. Here we get S2p minus S1p is equal to mu1 minus 1 into t. Consider this is equation number 1. From Young's double slit experiment, the relation for the part difference is given by, it is S2p minus S1p is equal to x into d by d. Here x is the distance between the fringe and the central bright fringe, and d is the distance between the two slits, and capital D is the distance between the slit and screen. So consider this is equation number 2. Compare equation 1 and 2. Here equation 1 is, this is equation on, that is S2p minus S1p is equal to mu1 minus t, and equation 2 is S2p minus S1p is equal to x d by 2. Compare these two equations. Here we get mu1 minus of t is equal to x into d by d, or x d by d is equal to mu1 minus 1 into t. So hence thickness of the sheet we can directly obtain here, that is t is equal to x d by d into mu1 minus 1. Consider this is equation number 3. For a constructive interference, we have a condition for part difference, that is part difference for a constructive interference is n lambda. So that is x into d by d is equal to n lambda, that is part difference is equal to, part difference is x d by d, so is equal to n lambda, where n is 0, 1, 2, 3, so on. So substitute the value of x. This x we can write as x is equal to n lambda into d by d. Substitute this value in equation number 3. So here we get t is equal to n lambda by mu minus 1. This is the expression for the thickness of the sheet introduced in between the source and screen. And the next concept is Lord's mirror. Lord's mirror is the arrangement of producing interference pattern using single slit. We have seen that in Young's methods, producing two coherent light source, we eliminate a pair of slits with a single source. Alternatively, another simple arrangement for producing an interference pattern with a single slit source is known as Lord's mirror. Just observe the diagram here. Here, the arrangement consists of plain mirror Mn. This is the mirror Mn. It is polished on the front surface and painted back at the back to avoid the multiple reflection. Here this front surface of the mirror is polished and back surface of the mirror is painted by black to avoid the multiple reflection. Light from the narrow slit, yes, this is slit as it is illuminated by the monochromatic source of light, is allowed to incident on the mirror almost at grazing angle. It is allowed to incident on the mirror almost at a grazing angle. The reflected beam appears to diverge from S2, and this reflected beam appears to diverge from the S2. This is S2, which is a virtual image of S1 act as a two coherent source. This S2 is the virtual image of the S1, and these two are act as the two coherent source. In direct case, the light that PS1Q and the reflected cone of the light, that is PS2B, is superimposed over each other and produce interference fringes in overlapping region PB. This is the overlapping region PB. Here we get interference pattern due to the superimposition of PS1Q and PS2B. It is found that the central zero order fringe is expected to lie at O, because we already discussed in a Young's modulus experiment, that is in Young's double slit experiment central fringe always bright. So here we are expecting at O we are expecting a bright fringe. So but the point O is outside the region. We can see here this interference is takes place in PB region, but this point is outside the PB region. So central fringe is not seen at this fringe pattern PB. So the central fringe may be visible by moving screen towards MN. Suppose we move the screen Y towards the MN, we may observe the central fringe. It is observed that instead of being bright, if we shift this Y towards the MN, instead of bright fringe, we are getting central dark fringe. This is clearly indicates that the light beam after reflection from the optical denser media, it undergoes phase changes of pi. It undergoes the phase changes of pi, or this pi leads the phase difference, and this phase difference leads the path difference of lambda by 2 between the two lights or a two beam. So this path difference leads the changes in the bright or dark fringes. So for a dark fringe, or when the point P, this point P on the screen, the path difference for the light to travel this from S1 to S2 to this S1 to S2 to point P is, path difference we can express as S2P minus S1P is equal to n lambda. Suppose we get this expression at the point P, means here we get the intensity of fringes is minimum. That means we are getting dark fringe because it changes the phase of pi, or a path difference is lambda by 2. So that's why we are getting at the point, if S2 minus S2P minus S2P minus S1P is equal to n lambda. Here at this region, that at the point P, we are getting dark fringe. Suppose if S2P minus S1P is equal to n plus half of lambda, that means 2, or we can write this as 2n plus 1 lambda by 2, then we get a intensity maximum and we are getting bright fringe. So at this point, any point here get if this condition is satisfied, means we are getting bright fringes. So the separation of the fringe width we can write, or a separation between the fringe width we can express as beta is equal to lambda into d by d, where d is the distance between the slit and capital D is the distance between the screen and slit, and lambda is the wavelength of source used, and beta is the separation between the slit, separation between the fringe or the fringe width. This is all about Lord's mirror, and the next concept is biprism. This is the schematic diagram of the biprism, Fresnel's biprism. It consists of two acute angle prism placed base to base. Hence, it is a single prism having a obtuse angle of 179 degree, and the other two angles are about 30 minutes each other. The prism almost appears a thin rectangular plate. We can observe here, this is the obtuse angle 179 degree. This is the two acute angle of 30 minute. So this biprism is constructed by a single glass plate by properly grinding and polishing the glass. So let's see what is the construction and working of the biprism. When a monochromatic, this is the schematic representation of the biprism. So this is the source S and this is the source S1 and S2. These two are the virtual source. The distance between these two is D. This is biprism. This is the screen. This point is the center of the fringe. So point is O. This is the screen M N, and the distance between this slit to screen is D, and the distance between the slit to prism is Y1, and the distance between the prism to screen is Y2. So here the monochromatic light through a narrow slit S, this is narrow slit S, is falls on the biprism. We divide into two component. It divides into two component. Here it divides into two component. One of this component is refracted from the upper portion of the prism. Here this component is refracted from the upper source of the prism by prisms, and it is appears to come from S1. This is S1, where the other of one is refracted to the lower portion. This is the other component is refracted through the lower portion and appears to come from S2. This is S2. This S1 and S2 act as a two virtual coherent source formed from the original source S. This is the S dash source, original source. These two are the virtual source S1 and S2. These two is produced by the source, actual source S, by the refraction from the upper and the lower portion of the prism. Thus, this S1 and S2 act as the two virtual coherent source here, and it is coming from, and it is version from the source S dash. Let light wave is arising from S1 and S2. It interferes in the in this region. It interferes in this region, this shaded region. So here we get the interference in this shaded region. So we can observe the shaded region here. We get the interference fringes is formed in this shaded region. We can find it on the screen ML. So this Fresnel biprism can be used to determine the wavelength of the monochromatic light that we used, and also we can find the fringe width of the fringes. So here the fringe width of the fringes we can express as beta is equal to lambda d by d. This expression we already derived in a last class, that is Young's double slit experiment. So just we adopt the expression of the beta from the Young's double slit experiment. Just go through the Young's double slit experiment, and here we take that direct expression, that is beta is equal to lambda d by d. And using this biprism we can find out the wavelength of the monochromatic light. So next, determination of the wavelength of the monochromatic light by using biprism. Just observe the diagram here. The narrow vertical slit, this is narrow vertical slit S, is adjustable width is mounted on the optical bench at a one end, and it is illuminated by a monochromatic source of light. This biprism is mounted close to the slit with its refracting edge parallel to the slit and facing to it. These are the parallel, and the position of the biprism is adjusted until two equally bright fringes of the slit are seen through the naked eye. So we have to adjust this biprism until two equally bright images of the slit are seen for the naked eye. Eyepiece, this is the eyepiece, micrometer eyepiece, is mounted at the some distance from the biprism. This biprism on the other end of the optical bench. This is the optical bench, and the eyepiece is focused on the fringe system. We have to focus on the fringe system observed here, and the fringe width beta is determined by the finding the width of the known fringes. We already discussed, that is beta is equal to d lambda by d, where d is the distance between the slit and the screen, and lambda is the wavelength of light used, and small d is the distance between the slit. This expression we adopt from the Young's double slit experiment. So using this equation we can easily find the wavelength of the monochromatic light. So this is the This lambda represents the wavelength of the monochromatic light used in the experiment. So therefore, if we want lambda means we can rearrange this beta equation as, that is, lambda is equal to beta d by d. This is the expression to find the wavelength of the monochromatic light. So student, today we discuss about the lateral fringe shift and Lord's mirrors and biprism experiment. If you have any doubt, just ask me.